Hello everyone. In the last video we had discussed about the introduction to the solid state. We had discussed about the basic things of defining a solid, its characteristic features, and then we have seen the differences between the crystalline solids and amorphous solids. Today we are going to see the type of solids or the type of crystalline solids that they exist. Let us see the classification of crystalline solids. So it is the classification of crystalline solids. These are actually of four types. The first one is molecular solids. Second one is ionic solids. Third one is the metallic solids. And the fourth one is covalent or network solids. So these are the mainly four types. Now, based on the bonds that they have. Now, let us discuss about one by one. See, molecular solids. Here, the constituent particles are molecules. That means molecules will join with each other to form the solids. And this is actually of three types. So this can be further classified into three types. The first one is the polar. Second one is non-polar. Let us make first one non-polar rather. Polar. And the third one is H bonded, means hydrogen bonded. So I can make it A, B and C because here already is 1, 2, 3, 4. So non-polar means the constituent molecules will be non-polar in nature. Say for an example, if we take solid helium. So as we know, between two helium molecules, there is no polarity. But if they form a solid, it will form a solid helium which is having non-polar nature. Means there is no polarity between them. In case of polar molecules, a very good example will be HCl. We know there is delta positive and delta negative. If it is solid, then only. So in case of solid HCl, what happens between hydrogen and chlorine, the polarity is already there. So if the bond is formed between the molecules, between two HCl for an example, between them, the polarity will be the major reason for the attraction force. Then there is hydrogen bonded. If I take ice, so obviously it is solid. So there, between hydrogen and oxygen, the polarity is already there. So if another molecule comes between these two, between this oxygen and hydrogen, there will be hydrogen bonding, and this H bond will be responsible for the attraction forces. So if it is solid, this will be called hydrogen bonded. The next one is ionic solids. Example is NaCl. Why? Because in NaCl there are two different kind of constituents, Na plus and Cl minus. So in case of ionic solids, one positively charged and one negatively charged constituent particles are arranged in a systematic manner to form the solids. In the video itself, you can see how it is done in this photo. Then the metallic solids. In the metallic solids, say copper and nickel alloys, what happens is, in a sea of electrons, few positively charged metals are there, few positively charged particles. So throughout the molecule, the sea of electrons are there, which are free electrons, that is why they can carry the electricity. And in between, the positively charged particles are there, constituent particles, which are called kernel. Then this is the covalent or network solid. Here, atoms are linked through covalent bonds. A very good example is diamond or even graphite. We know their structure. In their structure, you will understand how they are cross-linked and covalently bonded. So these are the classification of crystalline solids. During the video, I put the photos also where you can see by pausing them that how the structure is actually being done.
Now let us see unit cell. What is a unit cell? In case of an unit cell, you can see in a crystal structure, we know that the characteristic of crystalline solid is a regular and repeating pattern of constituent particles. Say this crystalline solid structure, it's a repeating pattern only. Now when we replace them, these particles will represent the points. Here you can see we have converted them into a points. This is called crystal lattice. Now crystal lattice is defined as the three-dimensional arrangements of constituent particles. Why it is a three-dimensional arrangement? You can see from this diagram. So represented diagrammatically it is. So it is in such a way it is represented that the particle is depicted as a point. So the arrangement is known as crystal lattice. So there are 14 possible three-dimensional arrangements. These are named after the famous French mathematician Bravais lattice. So we will put the picture of that also in the later part of this video. Now let us see how those 14 possible structures will look like. This is, you can see, rhombohedral, orthorhombic face centered, orthorhombic body centered, orthorhombic, monoclinic end centered, monoclinic, hexagonal, the cubic face centered, cubic body centered, and triclinic. So here you see, if we are talking about a crystal lattice, so the certain points will be occupied by the constituent particles, which we call the lattice point or lattice site. Then you see those lattice points will be occupied by atoms, molecules, or ions, depending on various cases. Now let us see this. Suppose those points are joined, means the lattice points. This is called the unit cell. Why it is called the unit cell? See, if they are being propagated, extended on every side, it is going to give rise to the complete crystal lattice. That means this is the smallest portion of the crystal lattice, which is this is called unit cell. If it is being repeated throughout, you can give rise to the complete crystal lattice, as you can see in this video. So this is called the crystal lattice, this shaded part. So we can say that the crystal lattice, here you can see the crystal unit cell. In the unit cell there are basically three edges, A, B and C, on X, Y and Z direction. The sides, you can say, or the edges, and we will have three angles also between between the edges, if we calculate the angles, it will be like this. Between B and C, we can call it alpha. Between A and C, it is beta, and between A and B, it is gamma. You can change this A, B, and C as your wish, but this is how it looks like. So 3 edges and 3 angles. Check it carefully. You can draw it in your copy for a better understanding. Better you pause the video and draw it. That will be best.
Now, let us see the parameters of unit cell. Since we had discussed that what an unit cell is in the small clippings, so let us define it once again. What is a unit cell? It is the smallest 3D repeating pattern. We need to understand this. It has to be a repeating pattern. That means it will be repeated of crystalline solids, which when repeated across different directions, means when the unit cell will be repeated along different directions, they will ultimately give rise to the complete lattice. That means actually how it looks. That means it's the smallest part, like the bricks in the wall. When it is being repeated, the total structure takes place. So let us see the parameters. In the parameter, two things. First is the length of the edges. That means these are the edges. If this one is A, this edge I am talking about, this one, and if this one is B, and if this one is C. So we have taken 3 edges, A, B and C. So if this one is B, this one is also B. So if we are talking about this angle, it is the angle between, remember this line is also C, this line is also B. So if we are talking about this angle between B and C, that means this angle, we can call it alpha. This is the alpha. Now, if we are talking about the angle between these two, that means this angle, this one, it will be the angle between A and C. We can call it beta. So this angle is beta. And finally, if we take the angle between A and B, this one that is, so this one is B, this one is A. If we take this angle, then we can call it gamma. So we have chosen 3 angles. One is alpha. So alpha, the second point, that is, alpha is the angle between, check it out, it is between B and C. Then the angle beta is in between which one? A and C. And if we take the angle gamma, it is between A and B. So you can change this A, B and C always. It is not necessarily strict. We do not put any kind of restrictions over here that this A will be this one only. You can take this one as A, this one as B, this one as C also. So in the different clippings, this one can change. The main thing is different edges, that is A, B and C. Between them the angles will be there, and this is the parameter. Based on these angles, we will have different kind of unit cells. Now we are going to see the type of cubic lattices. That means under this cubic system, there are 3 types of cubic lattices. First one is simple, second one is BCC, or it is also called body centered cubic unit cell, and the third one is FCC, that is face centered cubic unit cell. Now we are going to discuss about the structures in details. So for that, let us draw this cubic unit cell. This one. Here also. Let us draw 3 of them so that we can find out the differences actually. This one. So 2 we have drawn, and the third one also, let us draw it here. So 3 cubes rather we have drawn till now. Nothing more than that. 3 cubes only. So in order to understand the simple cubes, what happens is the atoms or the constituent particles are only present at the corners. Here only. Only present at the corners. They are only occupying the corners. Nothing else. So you can see 1, 2, 3, 4, 5, 6, 7, 8 atoms can be present. Not 8 atoms, the full portion of it is not there. We are going to see the calculation that actually how much of an atom is actually present within a unit cell. That is a separate discussion altogether. But you can see they are occupying the corners only. So we can say corners only. Here, body centered. So obviously on the corner, same thing will be there. The atoms will be there at the corners. So you can draw it. There are 8 corners. Same as before, no change. Only difference is this term body center, that means at the center of its body. In a cube, the center is this one. Precisely. Absolutely at the center, there is another cube, another atom. So this is called the body center atom. This one. Body center. So there are 8 atoms at the corners. Full portion of it is obviously not within the cube. And 1 atom at the center of it. In case of face center, see, when we talk about face, that means if this is a face, this one, this side, this is a face, on this side, the center of it, on the center of this face, there will be an atom. Let us clean this. First, as before, let us put the atoms in place at the corners. Since it is not body centered, so here there will be no atom. At the center of each face, there will be one new atom. So let us see how many faces are there. See, to understand how many faces are there, let us take this book. Check here. In this book, it is similar. This is one face. This one. This is another. This face. So if it was cube, then it would have been a center. Let's see, 1, 2, 3, 4, 5 and 6. So there are in total 6 faces. So in this center there will be one atom. Just on the opposite side, in the face center, there will be another atom. Then the below one, there is one atom here. There is one atom here on the above face. Then, so the 4 have been done. One is on your side, this side. So there also, this one, at the center of this face, which is at this position, there is another atom which is towards you, and which is opposite to you, this face, there is another atom. You can see these two are opposite to each other. Let us join them with different color. So these two are on opposite side, these two are on opposite side, and these two are on opposite side. So you can see these atoms are exactly situated at the center of the faces. So this is called face centered atoms. So this is how the 3 type of cubic lattices looks like. Draw the structure carefully. You have to practice it, because based on that the future numericals will take place. We have to have a very clear view of these structures. We have to understand it carefully, how it looks like, because the question from here on will be like, they will just mention that it is BCC, accordingly you calculate. It is FCC, accordingly you calculate. We will see the mathematical calculation afterwards, that if this atom is present here, whether the full part of it is within the structure or not. Apparently it looks like there are 1, 2, 3, 4, 5, 6, 7, 8 atoms. Whether actually it is, that is what we are going to see. But before that, you try to remember all these 3 structures, do practice it as many times as possible.